Hello, everybody. My name is Michele Torielli. First of all, I want to thank the organizer for giving this opportunity to speak. So today I will describe a new approach to computing chromatic and characteristic polynomials. And this is a joint work with my master thesis student, Madison Cox, that worked with me last year at Northern Arizona University. So this talk is divided into parts. In the first part, we'll talk about the hyperplane arrangement, and then we'll describe a special kind of family that are the arrangement associated with simple graphs. So let's start with the first part. So what is an hyperplane arrangement? To describe it, I first need to fix a field K that can be of any characteristic. In most of the time, it's probably of characteristic 0, but it doesn't need to be. In the second part of the talk will actually be the real number. And then I take S a polynomial ring with L variable that I call them x1, xl. So an hyperplane arrangement A in K to the L is nothing else than a finite collection, in this case of n hyperplanes. Each of them will have an equation in S. An arrangement is called central if each hyperplane contains the origin of K to the L. So basically, this can also be read from the equation of the arrangement, because I have that an arrangement is central if and only if it's described by the homogeneous polynomial of degree n, if I have exactly an hyperplane. Now, given an hyperplane arrangement, we can construct a new one. So the idea is this. I take A and I take H, an hyperplane in A. Then I construct the restriction of A to H. That is an arrangement that is denoted by A to the H that lives in H, but H is isomorphic to K to the L minus 1. So basically, I start from an arrangement in K to the L, and I go one dimension less. And so A to the H is nothing else than all the traces of the hyperplane on H, my chosen hyperplane. Now, when we study hyperplane arrangement, there are various approaches that one can take. So one of the first one that usually people look at is the combinatorics of the arrangement. And this comes from looking at the coset of intersection that is nothing else than a matroid. So what we do, we take L of A and we look at all the possible intersection of the hyperplane in A. So basically we start with the empty intersection. So I have the whole space K to the L. Then I have all the hyperplane, and then I start to intersect 2 hyperplane, 3, 4, 5, until I have no more possibilities. The thing that needs to be noticed is that this is a poset and is ordered by reverse inclusion. So I have that X is smaller or equal than Y, if and only if Y as a geometrical space is contained in X. The thing that we want to notice are the following. So first of all, L of A always have a unique minimal element that is the total space. And the second thing is that if A is central, then L of A is a lattice, because it also have a maximal element that is the intersection of all the hyperplanes. That so is a space that contains the origin. Associated with the poset, we can define the Mobius function. So the idea is that we want to define a function in a recursive way. So first we say that the Mobius function of the total space is 1. And then we compute the Mobius function of any intersection in the poset by basically doing an alternating sum of all the elements that are smaller than my given element x. With this Mobius function, we can define the characteristic polynomial of an arrangement A. That is nothing else than a sum of all the elements in the poset, where we use the Mobius function and we multiply the Mobius function of x by t to the dimension of x, where t is in indeterminates. And in this way, we get a polynomial in Zt. And it's actually a polynomial of degree n. Now, the characteristic polynomial has a lot of nice property. In particular, it satisfies this formula. So if I have an arrangement A, I can compute the characteristic polynomial of A by deleting one hyperplane and then restricting to it. So basically, I have the chromatic polynomial of A is the chromatic polynomial of A, where we have deleted one hyperplane H, minus the chromatic polynomial of the arrangement obtained by restricting at the same H. So this should remind quite a lot of people about the formula that we have for the chromatic polynomial of a simple graph. And we will see exactly that there is a very strong connection. The other thing that is important to notice is that from the chromatic polynomial, we can read quite a lot of things about the arrangement. So for example, if I have an arrangement on a finite field, basically the number of points outside my arrangement can be computed by evaluating my characteristic polynomial of Q. Instead, if I have a complex arrangement, I can compute the topological Betti number of the complement that are in general hard to compute by looking just at the coefficient of my characteristic polynomial. Finally, if I have an arrangement in real space, we can compute the number of chamber and bounded chamber by just evaluating our chromatic polynomial at -1 for the total number of chambers. Then obviously I need to take an absolute value, and at 1 for the number of bounded chamber. So we know what we are talking about. A chamber of an arrangement is nothing else than a connected component of the complement, and I will call it bounded. Is actually, as a space, is bounded itself. Now, in general, computing characteristic polynomial is quite hard. And even if one wants to find a way to compute, for example, a number of chambers without computing the characteristic polynomial, also this is quite a hard enumerative problem. So it's always welcome if we can find new ways to compute the characteristic polynomial or the number of chambers. The fact is that in this talk, we will describe a new method for computing the characteristic polynomial, and hence we will find a new method, a new ideas at least, to compute also the number of chambers. So let's start with a simple case. If I take an arrangement A that is central in R3, and I take an hyperplane that is not in A, and then I can easily compute the characteristic polynomial of A, where I've added this new hyperplane, by knowing the characteristic polynomial of A, because we have that I just need to subtract this polynomial, that is t squared minus kt plus k minus 1, where k is nothing else than the number of distinct lines in the intersection between h0 and all the hyperplane in A. So the idea here is the following. I want to find a way for which, if I know the characteristic polynomial of A, I want to add one hyperplane, and I want to be able to sort of control how this characteristic polynomial change. And the thing that has to be noticed is that in this case, this comes directly from the addition-deletion formula. But in general, it's actually a hard task. So the fact is that for today, and that's what we did with my student, I will focus on a special kind of graphs that are the graphs that come, the arrangement that comes from graph. So I take G, a simple graph with vertex at V that I wanted to be denoted numbered from 1 to L. And in this way, I can define an hyperplane arrangement AG in K to the L, L exactly the number of vertices, where for every edge, ij, I have a corresponding hyperplane xi minus xj. And the nice thing that we have is that if G is a simple graph, I have that the chromatic polynomial of G is equal to the characteristic polynomial of the associated graphic arrangements. And so that's why the formula we saw before about adding or deleting one hyperplane and restricting should seem so familiar to many people. Now, let's see one example. If I have this graph on 5 vertices with 6 edges, I will have a corresponding arrangement in K to the 5 with 6 hyperplane arrangements. So for example, I have the edge 1, 2, then I have the hyperplane x1 minus x2 equals 0. Then I have the edge x2, x5, 2, 5, and then I have the hyperplane x2 minus x5 equal to 0. And then, obviously, if I compute the chromatic polynomial of G or the characteristic polynomial of the arrangement, I obtain the same thing. That is t minus 1 squared, t minus 2 squared. Now, let's recall the chromatic polynomial of two known graphs. The first one is a tree. So every time I have a tree on L vertices, its chromatic polynomial is t times t minus 1 to the L minus 1. And every time I have a cycle graphs, again on L vertices, I can compute its chromatic polynomial with this formula. So it's t minus 1, and then a sum of alternating things where basically everything depends only on powers of t minus 1. Now, to describe our approach, we need to first introduce a new kind of subgraph. So if I take G, a simple graph, and H, a subgraph of G, then H is called path intersecting. Basically, if every time I take two vertices of H that are non-adjacent in H, then every possible path that goes from Vi to Vj or Vj to Vi, obviously, this path needs to be completely contained in H. Why do we want this kind of subgraph? Because in this way, we could prove that if I take G a graph, a simple graph, and H a path intersecting subgraph, then the chromatic polynomial of H divides the chromatic polynomial of G. Just consider that in general, if H is not path intersecting, this is not true. I can find many graphs that are induced or have other property for which the chromatic polynomial of H does not divide the chromatic polynomial of G. So let's see also here one example. If I take this graph with 5 vertices, I can consider S the set 1, 2, 3, 4, and then I can look at H. That H is what? Is just a 4 cycle, is the 4 cycle 1, 2, 3, 4. Then I have that the chromatic polynomial of H is t minus 1 times t squared minus 3t plus 3. And then I can actually compute straight away, this is reasonably a small graph, the chromatic polynomial of G, that is this one, t minus 1 times this polynomial of degree 3. And then it's clear that the chromatic polynomial of H does not divide the chromatic polynomial of G. And what's the problem here? Here the problem is that H is not a path intersecting subgraph, because I have the path 2, 5, 3 that joins the vertices 2 and 3 that are non-adjacent in H, and this path is completely outside H. So that's where the problem arises. Now, the idea is that the other thing we can do, and is useful for our construction, we want to generalize the notion of a clique sum and consequently of the clique sum theorem. And so the idea is following. I take two graphs that have two subgraphs that I call, that are induced in this case, that are induced by the subset S1 and S2. And in this way, if I have that these two induced subgraphs, G1 S1 and G2 S2 are isomorphic, basically I can glue the two graphs over this new subgraph. And the idea is I can obtain V, a new vertex set that is nothing else than the union of V1 and V2, where we have identified the set S1 and S2. So now this has cardinality, the cardinality of V1 plus the cardinality of V2 minus the cardinality of S2. And then I take all possible edges, throwing away multiple edges and loops. So in this way, I obtain a simple graph that we will call the subgraph sum graph along these subgraphs. Now, the point is that if G1 S1 was a clique, this is exactly the clique sum of two graphs. Similarly, we could generalize the clique sum theorem. So the idea is that if I have two graphs and basically I glue them along a subgraph, but I need to assume that the subgraph H1 of G1 is path intersecting and the subgraph H2 of G2 is also path intersecting, then I have a generalization of the clique sum theorem. And in fact, we have that the chromatic polynomial of the subgraph sum of G1 and G2 along H1 is nothing else than the chromatic polynomial of G1 times the chromatic polynomial of G2 divided by the chromatic polynomial of this common part. Now, the idea is I want to start from a graph. I want to assume I know the chromatic polynomial of this graph, and I want to add one edge in such a way that I know exactly how the chromatic polynomial will change. First of all, if I add one edge in a way that doesn't add any cycle at all in the new graph, then I have that the chromatic polynomial of the new graph is obtained from the chromatic polynomial of G multiplied by t minus 1 divided by t. So this is quite easy. Similarly, if I obtain the new graph by adding one edge, H0, in such a way that this H0 creates only one cycle of length m, again, I can easily compute the chromatic polynomial, because I have the chromatic polynomial of the new graph is the chromatic polynomial of G times the chromatic polynomial of the cycle graph that we saw it before, divided by t minus 1 to the n minus 1. The fact is that in order to prove these two theorems, it was essential to generalize the clique sum theorem. Let's see one example. So if I consider G, the graph on the left, so I have 5 vertices and all these edges. So how do I compute the chromatic polynomial with this approach? I first compute the chromatic polynomial of a spanning tree that we saw what it is. And so is a t minus 1 to the 4. Now, obviously, this is unchanged for whatever spanning tree I pick. And then I start to add edges one by one. So, for example, here, I can first add the edge 3, 5, then 1, 4, and then finally 2, 4. In doing so, at each stage, I'm creating one single tree cycle. And so the formula we had before allow me to control what the chromatic polynomial is going to be. So at each stage, I'm taking the chromatic polynomial of t and I'm multiplying by t minus 2 divided by t minus 1. So this means that the chromatic polynomial of g now is t minus 1, t minus 2 to the 3. One thing that needs to be noticed is that, number one, this path is not unique. I could have added, for example, first 1, 4, then 3, 5, and then 2, 4, or in other order. And this is unchanged. And the other thing that needs to be noticed is that there are situations where I'm forced to add one edge that create more than one cycle. So what do I do in that case? In that case, I just realize one thing. If I know exactly what kind of cycle I'm adding, basically I'm focusing on a path intersecting subgraph. And so if I know that I have a path intersecting subgraph, I can use the theory we described before. So where basically I know that if I have a path intersecting subgraph, the chromatic polynomial of my subgraph divide the chromatic polynomial of my graph. And using this approach, we can always compute the chromatic polynomial of any graph as big as you want. So thank you for the attention. And so this is the reference to the article we posted on arXiv.